Hey everybody, welcome back to Fastware. I want to start today by saying thank you to everybody who over past week or so engaged with my videos, asked questions, commented, provided criticism. It was a truly great interaction with our community, with the discussion. I'm very happy to see such a big group of people who just eager to learn and improve and engage. It was a truly phenomenal experience for me, and I want to thank every single one of you who subscribed and watched my videos. So with that out of the way, as usual, I would like to take an example which I found on the internet, a challenge, so to speak, and look if we can implement it in several different ways and compare the performance of how it compares, kind of a standard implementation, sort of a naive implementation, maybe more of a on the expert side. So I just found the example on this a bit challenge. And the problem goes like this: replace letters with the positions in the alphabet. So create a function that takes a string and replaces each letter with its appropriate position in the alphabet. A is for 1, B is for 2, and C for 3. And you introduce space after each of them. Following, so both uppercase and lowercase letters are treated exactly the same. And if it's any other character, you just ignore it. So as you can see, here are some tests and results that I took from that website, and I will leave the link to that challenge in the description, so you will be able to go find it yourself and maybe try it out as well. So here it is. So you can see we have wow and goes 23 space, so W-O-W, then D, then what is it? O, and then E and S, right? So, and this is how that output is produced. It's fairly simple. So what I started with is sort of a very simple implementation to get my head around the problem. I called it the naive implementation, where I basically took a string, just reserved it, some space, and then wrote a massive case statement. And I thought, why not? It's very naive. It's very kind of a simple to do. So I did that, and then obviously removing last space character and then returning a result. So this was my first attempt. Now, since I verified that this implementation works, and then I say, okay, so how a kind of a practicing software developer would do it, So I thought, okay, I think this is how I would have approached it probably 5 years ago or so, halfway through my current career. I've been in software engineering for about a decade, so yeah. So anyway, so this is how I probably would have approached it, saying, okay, so if it's from A to Z, blah, 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 then I say take that character and minus A, add +1 because the A is supposed to be not at position 0, but at position 1. Exactly the same thing. And then append a space, and then just append it to a result. I'm still reserving, still erasing the last character, so only the core algorithm is different. Instead of a switch statement, now you have this if-else here doing that. So I implemented this, compared that, actually checked that the output is correct as well. And then went and to see how I would do it now with all the knowledge that I have about software engineering, performance, and whatnot. And this is what I came up with. So I introduced a value from 0 to, indexes from 0 to 25, representing 1 to 26 characters. And again, that part, you're introducing a string, you reserve it, and you remove the last character. This is still exactly the same, so only the core loop changes. And here what I do is I just pick up the input. I immediately convert that character to an unsigned, and then minus the A character. So A is 97. So imagine what would happen. Let's say you have 98 minus A, that would be 1, right? But if it's out of the range, like if it's, for instance, if the character here is, let's say 20, you do minus, that will produce, because of the modulus arithmetic of the unsigned integers, what you would get is it will wrap around from negative number to a very large positive number. Well, very large depending on the type, but yeah. And then I produce a lowercase character, so the value for lowercase, and then I do exactly the same for uppercase, one after another. I'm not discriminating what it isn't, and then I do a minimum. So a minimum, this is from bit twiddling hacks from I think Stanford University or something. It's an awesome thing. It shows you how you can basically use bit manipulation to perform common operations like minimum, maximum, some basic finds and whatnot, without needing for branches. So because we know how to do the minimum with branches, it's very simple. But this is an example of how to do it without branching, and it is awesome. So here it is. So I basically now take a minimum. So why does this work? So you have lowercase. So let's say we have character B, a lowercase character B. So this lower should produce value 1, right? Because A is at 0, B is at 1. And then when you wrap around here, this will produce, again, so because lower cases are higher in the ASCII table, this will produce a much larger number. I don't know, something like in 30s, so 32 or something like that. So, and I'm just taking the lower of 2. Say, okay, this produced 2, and this produced 32, let's say. Just a guess. Don't hold me to that. That says, okay, so I'm gonna take 2. And I say, great. So if 2 is less than 27, so because we have 0.26 allowed, then we'll basically look up in our map for position, for instance, 1, which in this case will be this 2, and we say pick up that and just insert that string directly into our result. So this is how this core loop works. I think it should be fine. I tested it with all the inputs exactly like any others. And here I'm about to show you some results. So I have the naive, the pro, and the expert implementations, and here are basic output. So we have about 3,600 nanoseconds, so about 3.6 microseconds to run this particular implementation with naive. This sort of a experienced programmer is actually much slower, and it's a good thing to understand that just because you can write a code like that doesn't mean it's going to be faster, because you have to perform quite a bit of operations. Here it does 2 forms of append, which is so string appending is super expensive. We don't want to do that, generally speaking. So string concatenation is not great. Avoid in your code as much as possible. So yeah, so we do, because of the way this loop is constructed, so you have 2 ifs, which if the first one doesn't work, you need to always check the second one. So you have a lot of comparisons and a lot of string concatenation, sorry. And for that reason, the performance of this particular code is not particularly good. And we can see that the expert implementation, which I would write now, is, what is it, about 15% faster than the naive implementation, and quite a bit faster than the professional software engineer's implementation. So with that, I hope I explained my thought process in approaching this problem. It's a small one this time around. I was a little busy with other stuff. However, if you liked what you saw, want to see more, please subscribe to the channel, like this video, comment, as usual, engage. I love it. It's awesome when you do that. Have a lot of fun in interacting with you guys. And yeah, I hope you liked it, and I'll see you next time. Have fun writing fast code. Cheers. Bye.